we can consider this linear system here. And note that if we're interested in the trajectories, we'd have to solve this first order nonlinear differential equation. And we could take the approach of making a substitution. We could make the substitution that u is y equals over x. And we could reduce this back to a separable dE. So in principle, this will always work for finding the equation of trajectories from linear systems. But the devil's in the details, right? To actually solve this dE, the details could get a little messy, right? In this particular case, you'd have to complete the square, do a trig sub, all those things you hated doing from Calc 2. Other problems, the details could be worse. It could be partial fractions, or you may not even be able to come up with an expression via anti-differentiation. So it works in principle. In practice, it could be a little trickier. So we're going to introduce another approach here. Now, in this approach, we are going to assume that an implicit solution exists. So we are going to assume that there is some implicit function h of x and y that will satisfy this differential equation. Now, as soon as we have implicit solutions, we are talking about functions that have two variables. Now, unfortunately, to deal with techniques like this, sometimes we need to bring in multivariable calculus. The chain rule for a function of two variables like this, and remember that y is really a function of x here, if we were interested in taking the derivative of this expression h of x and y, we'd have to use a partial derivative with respect to x, then dx dx, partial derivative with respect to y, dy dx. Now, this is equal to 1, and that means we've got the following: dh dy and dy dx. Now, we're going to take a second, and we're going to compare this to our trajectory equation. So our trajectory equation looked like this. And what we're going to do is say, hey, look, there's a dy dx, and here's a dy dx. I'm going to rewrite this. I'm going to rewrite this as 2x plus 8y times y prime of x. And then I'm going to bring this expression in the numerator, I'm going to bring it over to the other side. So it will be x plus 2y in a bracket. This I'm going to compare directly with this. And if I overlay them like that, what I'll get is the following. I can see that I'm able to come up with a way to find h. And this gives us a system for h. What we'll get is these two terms and these two terms should be equal. And if this is the case, in fact, what we're going to find here is that d by dx of h and x and y really should be 0, which implies that h of x and y is a constant. So the trajectory equation itself kind of validates that, yeah, there should be an implicit solution here. So this works if I get these two conditions met. dh dx is x plus 2y. dh dy is 2x plus 8y. What this is, folks, is a system of first order partial differential equations for h of x and y. This is a system of first order PDEs for the function we're looking for. And it kind of makes sense that they should be partial differential equations because it's a function of two variables. So what we have to do is we have to solve this by a technique known as partial integration. You might say, what on earth is partial integration? We take either one of these equations, and because there's a partial derivative, we are going to anti-differentiate with respect to x. I'm going to take both sides and anti-differentiate with respect to x. That means x is the integration variable, everything else is a constant. This is going to return us back to our function. This will get us an x squared over 2 plus 2xy. And now here's the difference. Normally when we perform a single variable integration, there is a constant. But this time it's not a constant. It is an arbitrary function of y. So remember, because we did a partial derivative with respect to x, any function of y is going to be treated as a constant. And so if I were to differentiate this thing with respect to x, it would just give me a 0 and return me back to the line above. And that's the key difference. So this partial integration allows me to get something for h of x and y. Now what we're going to do is take a partial with respect to y and compare it to the second equation. So if I take this expression and I partial differentiate with respect to y, that basically means anything with a y will be differentiable. Everything else is a constant. And we'll get 0 plus 2x plus c prime of y. Now if we go up above, we're going to compare this to what we should be getting for our dh dy. And what we should be getting is a 2x plus 8y. And that means that c prime of y has to be 8y, and that means if we were to integrate this or take the antiderivative, we would get 4y squared plus an honest-to-goodness constant. And voila, we have found it. H of x and y, the implicit solution, is x squared over 2 plus 2xy plus 4y squared. And we need this thing to be equal to some constant. Now, it doesn't matter if that constant's on one side of the equation or the other side. We are going to be talking about its level curves. And this is the point. And what this expression is right here is a rotated ellipse. And if you're seeing this picture, this is an overlay of the slope field of this system along with this equation. Now, this particular level curve comes from the initial conditions. X of 0 was the point 2 and negative 1. So if you look at this picture, there is in fact a point right there at 2 and negative 1. If I were to plug in 2 and negative 1 into this expression, I would find that the value of k would be 2. So this is the level curve, h of x and y equals 2. And that's what we'd see here. You pick a different value of the constant, you get a different level curve. And either one, they will all have to be these slanted, rotated ellipses in order to have this work. Now, this seemed pretty lucky, right? It seemed pretty great that we could just take our differential equation and rewrite it, and it all worked out like this. So this is something that we would call an exact DE. The trajectory equation was exact. And when we say exact, it means we could write it as the derivative of some two-variable function equal to 0. We could rewrite the DE like that, and that's exactly what we did. Now, of course, the question is, when will this work? Will it always work? The answer is no, it won't always work. Here's what we need. We need to be able to rewrite the DE to rewrite this thing, we had y prime of x is equal to some function of x and y. We need to be able to rewrite it as the following: g of x plus y times some little h of x plus y, y prime of x equals 0. We need to be able to rewrite it in this form. And then when we compare it to the total derivative here, this thing has to be dh dx, this thing has to be dh dy, and there's a y prime of x there. So we need this to be true. dh dx equals g of x and y, dh dy equals little h of x and y. So again, perhaps a better way to see this here would be to realize that you could write this thing as a fraction here. So you could write it as g of x and y over h of x and y. And then you could separate that all out. Now, there's a theorem from multivariable calculus that says if you've got nice, well-behaved functions like we are going to assume we have here, then when you take higher derivatives that are partials, it doesn't matter what order you take them in. So if I were to take the second derivative of this first expression, so if I have an x derivative, if I take a y derivative, I'm going to have dg dy. Or another way we would write this would be this mixed partial would be dg dy. And if I were to take the x derivative of this side, so dh dx, then the mixed partial that I get has to be the same regardless of what order I take them in. That's the result of this theorem. So we need dg dy to be dh dx for this to work. And another way of saying it is for this trajectory equation to be exact. So this is what's called a test for exactness. Now you might say, well, isn't this always going to be true for every system we do? The answer is no. So the equation that we were just solving, negative x minus 2y, 2x plus 8y, the thing upstairs, up here, this is our g of x and y, and this thing in the bottom is our h of x and y. If we rewrite this, what we'll find is that x plus 2y plus 2x plus 8y is y prime of x. That's going to give us a 0. Of course, we want this to be dh dx, dh dy, y prime of x. So if we were to take this y partial derivative, we'd get 2. If we were to take this x partial derivative, we would get 2. So this dE is exact. It works out. But if we go to the first, another equation, so this was in a previous video, if we were to take this particular equation, we would rewrite it to test for exactness. So we would put everything up on one side, set the equation equal to 0. This would be dh dx. This would be dh dy. We would test the exactness. So we would take the y partial derivative of this. We would get a 1. We would take the x partial derivative of this. And here we would see we'd get a negative 1. So this would not be an exact equation, and we would just rely on the substitution or some other method like we did before. So exact equations are kind of helpful. It gives you a way to approach things as an alternative. Sometimes the details will be very quick and easy, like in this previous example with the ellipse. Sometimes it won't be worth your trouble. Now, the main use of these exact equations is in not really for determining trajectory equations. but for something else. Hamiltonian systems in nonlinear mechanics. So physics people love exact equations. When we get to a little bit later in the course, we'll be talking about nonlinear systems and things called conservation laws. So you've probably heard of things like conservation of energy. Well, exact equations pop up there. So it's a technique that's worth investing in now because we'll need it later.